So now what we have to do is first so each of this term we vaguely saw that each of this term is corresponded to the orientation. But exactly what we want to do is count the number of even circulation and odd circulation and the difference, which is not quite same as the number of ways to orient an undirected graph. So we have to make the connection between these terms and the circulations. That's one. And then we have to, try to understand when does this polynomial vanishes? When does it become zero? So let's first prove the connection between these terms and the circulation. So let's define on H Vi Vj, which is directed edge, in an orientation of G. Let's say this is decreasing. If I is big and j is smaller. So V2 to V1 is a decreasing edge, but V1 to V2 is not decreasing. Then we say the parity of an orientation of G is the parity of the number of decreasing edges. So the connection between this term, each term, and the orientation is clear. So now we want to find the So we will first establish the connection between these two, and then we want to find the connection between this orientation and circulation. So the way of orienting G is that you orient all the edges, but to take the circulation, you delete some edges and then you orient the remaining one. So first, let's establish the relationship between orientation and the term. So let D be the vector D1 to Dn of non-negative integers. In the graph polynomial P sub G, the coefficient of the monomial let's say you take the x1 to x1 to d1 times x2 to d2 times xn to dn is the coefficient is exactly the number of even orientations of G with say out degree sequence D minus, so this is 1, minus the number of odd orientation of G with out degree sequence D. So you take all the orientation which has parity even and you count all the odd orientation with a specified out degree and you subtract, then that's the coefficient. proof is actually simple. So we know that the polynomial is homogeneous polynomial because you have like xi minus xj, xi, let's write it with number, x1, x3, x2, x5, x4, x5, and so on. So each one of them is homogeneous of degree 1. And then how many terms are there? There are number of h many terms. And you multiply that. So the polynomial is homogeneous of degree EG. And each monomial, say each contribution to the expansion is formed by selecting one endpoint of each h. This is, we choose this, and then multiply, then that's each monomial. And this corresponds to an orientation by letting the selected vertex be the source of the edge. So meaning V1, V2, V3, V4, V5. Then if you choose these, terms, that means you will orient from 1 to 2, and 1 to 3, and 5 to 2, and 4 to 5. So this gives you an orientation. The resulting contribution to the expansion is -1 to the t. So you count the number of times that we selected the bigger one, that's t. Because this term is negative, this term is positive, so you multiply negative term this many times. And then also, we are now counting the contribution of this term. So we only count the choice, which give us, this times subconstants. Then that means we choose x1 exactly t1 many times, and we choose x5 exactly t5 many times. That means in this orientation, V1 has out degree t1, and V2 has out degree t2, and so on. So where this ti is the out degree of vi in the corresponding orientation, and t is the number of decreasing edges. So if you choose this, that exactly corresponds to this decreasing edges. So t is the number of choices where you choose this negative term, which corresponds to the decreasing edges. So for a given list t of out degree, the even orientations count +1, because t is even, then this is +1, and the odd orientation count -1. So which proves that this holds. So this lemma provides the connection between this term, the coefficient of this term and the orientation. And then now we want to make the connection between the number of circulation and number of these even and odd orientations. So for an orientation, what we want to show is that, let's say D is an orientation of G with, say, Di is the out degree of vertex Bi in this digraph T for all vertex vertex Bi. The absolute difference of absolute value, then absolute value of the coefficient of this monomial in PG is same as the absolute difference between the number of odd circulations in G and number of even circulations in D. So this is not G, this is D. So we just show that this corresponds to the number of even orientations and odd orientation of G. And this is one specific orientation. So we want to make the connection. So we fix the orientation D and let D prime be an arbitrary orientation of G with the same out degree sequence. So our goal is to, for each D prime, we want to correspond it to circulation inside D. So if you count all such D prime, and then we count, the ones which are even and the ones which are odd in terms of this parity of orientation, the number of decreasing edges, then that's exactly giving the difference of that is giving the coefficient. And then we want to connect it into the number of circulation inside D. And let D plus D prime be the spanning subdiagram of D whose edges are those oriented in an opposite way in D and D prime. So for example, if we have, say, D in this way and D prime in this way, then these two are the edges which are oriented in different way. And we take the subdiagram of D. So this is oriented this way and this is oriented in this way. Then what do we know? This is actually a circulation because we know this, 2D and D prime has the same out degree for all vertex P. The subdigraph D O plus D prime is a circulation which is contained in D. Because here we know that the vertex B has out degree 4 in D. And then in D prime, it also have the 4. And if we know that this red, graph has out degree 1, meaning that in D prime, this is incoming edges. So it has 4 outgoing edges, but 3 of them coincide with D, but 1 didn't. That means there must be this 1 outgoing edges, which doesn't coincide with D, meaning that this must be incoming edges in D. So it gives us incoming edge in this red graph as well. So as long as you have 1 outgoing edge, you have incoming edge. By the same logic, as long as you have 1 incoming edge, you have 1 outgoing edge. So at every vertex, you can show that in this D O plus D prime has the same out degree and in degree. Out degree and in degree at the vertex are same. So this is a circulation contained in D. Also, each edge placed in this changes the parity of the number of decreasing edges. So if this has even number of edges, then it's if and only if the number of decreasing edges in D and D prime has the same parity. If and only if means that if this has even number of edges, then they have the same parity. If this has odd number of edges, then it has different parity. So switching the orientation on the edges in a circulation does not change the out degree. At any vertex. So this inverts the map sending D prime to this. So meaning that we fix this D and then we consider all the set of D prime which has the same out degree sequence as D. And for each of them, we send it to a circulation. And this is a map. And we can consider the inverse map. Inverse map that if you have this circulation C inside of D, let's say this is D, and then you take this, you take this circulation and we flip this orientation. Then you get a new orientation, which is D prime, which is within this set because, let's say, D double prime, which is within this set because it has same out degree as D. And then it's, actually the inverse map. You take D and then you go to this circulation, and then you use this circulation to invert the orientations in D, then you come back to D prime. So this is actually bijection. We thus have a bijection from the set of orientations with the same out degree as D to the set of circulations contained in D. So what do you have? You have this set of orientation same out degree as D, and set of circulation contained in D. You have one-to-one correspondence. Moreover, as we shown it here, you divide into even circulation and odd circulation. And here D, which has same parity of the number of decreasing edges as D and different parity as D, then this actually gives us bijection on entire thing, which maps this part into this part and this part into this part. So by this, as we have observed that the parities of orientation and the corresponding circulation are the same, hence the coefficient has the claimed value. So this, which is the difference between the number of odd orientation and even orientation minus the odd orientation, and this is the number of, difference between number of even circulation and odd circulation, and they are the same. So this gives us the relationship between graph polynomial and the number of circulations. And now and also one thing to note here, this is irrelevant of D. It's only relevant with this sequence Di. So we know that this difference of D is only depends on the half degree sequence of D. And now what we want to prove is that if this is non-zero for certain D, then what does it mean? Then now what we have is in this graph polynomial, if you expand it, at least one term has a non-zero coefficient. So that's what this diff of D is non-zero. So now what we want to do is that if PG has a non-zero term, then PG is non-vanishing for some evaluation at numbers chosen from the vertex, color list. So each vertex, so we are talking about list chromatic number. So each vertex we have a list. So 1, 2, 3. So here 1, 5, 7. So some numbers are available here. And then what we want is once you assign this color to each vertex, then that's the same as assigning this value to the variable, which is corresponding to the vertex. And then for there, if this P of G is non-vanishing, it has value non-zero, then our choice is proper coloring. So what we want to do is we want to show that for some evaluation, for some choice, if we choose the number from each vertex list, then this PG is non-zero. That's what we want to show. And then the condition D is non-zero is same as that it has at least one non-zero term. So this is our goal. So once we show this, then we are done. So this is our next goal. So in the next video, we will prove this.